In this lecture, we will be talking about mass balance problems in which the product from a reactor is sent to a separator where the unreacted reactants are recycled back to mix with the fresh feed to the reactor. The products are removed as well from the separator, and if there are any inerts in the feed, the fresh feed to the reactor, those too would have to be removed. Those inerts can either be purged from the recycle stream as shown here, or they could be removed from the product stream, which is not shown here. For the problems we're going to work in this lecture, there are no inerts in the feed, so we don't need to worry about purging the inerts, and the stream does not exist. For a problem like this, there are multiple choices for the control volumes we can use to perform mass balances. As shown here, the first control volume, indicated by the red dashed line, surrounds the whole process. And looking at this control volume, there is one input stream, that's the fresh reactants, and there are two output streams, the products from the separator and the inerts that are purged from the recycle stream. Another choice for a control volume to perform mass balances is indicated here as number 2. This would be mass balances around the mixing point, where the recycled reactants are mixed with the fresh reactants. A third control volume choice would be around the reactor. We have one stream coming into the reactor, our feed to the reactor, and one stream coming out, our product. We've been working problems most recently that involve mass balances around the reactor alone. The fourth choice for a control volume would be around the separator. We started off doing mass balances for processes in which we only had a single unit operation, such as a separator. In this particular example, we have one input to the separator and two outputs, the desired product stream, as well as a stream containing the unreacted reactants, which will recycle back to feed to the reactor, and potentially purge a portion of that stream to remove inerts that might build up in the process. For each of these 5 there's one other control volume we could consider. That would be a control volume around the split here, where we split the recycle stream into 2 streams. One would be a purge stream in which the inerts are removed, and the other is a stream that is recycled back to mix with the fresh reactants. We can perform mass balances for any of these control volumes. If we perform mass balances for any control volume that involves a reactor, then we're going to use atomic balances to perform the mass balances. For all other control volumes, we're just simply going to use molecular species balance. So control volume 1, the overall one, contains a reactor, so we would use atomic balances for that. Control volume 3 is around the reactor alone. We will use atomic balances for that. Now remember that if we use a species balance around a split point, such as that shown here for control volume 5, is that there's only one independent mass balance that can be written for a split. We've introduced quite a bit of new jargon for mass balance problems that involve reactors, and we'll review that terminology here. Then we introduced 2 new pieces of terminology related to processes such as we've just drawn, in which there's recycle. So let's talk about the jargon we introduced for reactors in which there's only a single reaction. We first talked about the limiting reactant. That's the reactant that has the smallest extent of reaction if we set the moles coming out of the reactor equal to the number of moles that enter minus the stoichiometric coefficient in the balanced chemical equation times the extent of reaction xi. We set that all equal to 0. Or we could just simply compare the ratio of the number of moles entering into the reactor for species I to the number of moles that are entering for species J to the ratio of the stoichiometric coefficients to determine which of the species is the limiting reactant. Fractional conversion we calculate as taking the difference between the moles fed of a species and the moles that exit, which is equal to the moles consumed, and then dividing that by the moles fed. So fractional conversion is the moles consumed divided by the moles fed. Fractional excess we calculate for a reactant that's in excess. That's equal to the moles fed minus the moles stoichiometric, that is the moles of this excess reactant that would be consumed if the limiting reactant was consumed completely. So we'll take the difference between the moles fed to the reactor and the stoichiometric number of moles that would be needed to react completely with the limiting reactant. Take that difference divided by the moles stoichiometric in order to get the fractional excess. When we have multiple reactions, we introduce two new terms. The fractional yield is the moles of the desired product by the moles that would be produced by a stoichiometric consumption of the limiting reactant. This moles stoichiometric is the moles of the desired product that would be produced if the limiting reactant was converted completely to the desired product. The selectivity is the moles of the desired product that's produced divided by the moles of the undesired product. Now, we've worked with these two terms in problems recently, these two pieces of terminology. When we have recycle back to a reactor of unreacted reactants, we're going to talk about two types of conversion. The first is single pass conversion. This is equal to the moles that are fed to the reactor minus the moles that exit for a species divided by the moles fed for the reactor. If we talk about an overall conversion, we're talking about the moles that are fed for the process minus the moles that exit from the process. These are the moles that are fed if we look at an overall control volume. And these are the moles that exit based upon the overall control volume divided by the moles that are fed. So this overall conversion is the moles that react within the overall control volume divided by the moles fed. So we're going to apply some of these new ideas and do some mass balances for this problem here. In this problem, methanol, which is CH3OH or CH4O, we're also going to use the letter M to represent methanol, is produced by reacting carbon monoxide, CO, with hydrogen, H2. And we use the letter H just to represent hydrogen, the hydrogen molecule. A fresh feed of CO and hydrogen joins a recycle stream and is then fed to the reactor. The reactor effluent is sent to a separator where it's cooled to produce a liquid stream of pure methanol. It also produces a vapor that contains CO, hydrogen, and methanol that's recycled to the feed. This stream is mixed with this fresh feed stream here. What I'd like for you to do is pause this presentation, this lecture, and draw a label, a process flow diagram, assuming first that the reactor effluent flow, the stream that immediately leaves the reactor, has a flow rate of 350 moles per minute, and its composition is 27.3% CO, 63.2% hydrogen, and the balance methanol. Now this is on a mass basis. This is going to cause a little bit of a problem because the flow rate is given in terms of moles. So we're going to have to convert these mass fractions to mole fractions. I also want you to assume that the recycle stream contains 0.4% methanol on a mole basis. There's no conversion required for this, but there will be for the first set of compositions that are given here. So what I do now is pause the presentation, draw the process flow diagram based upon the description here, and label the streams with molar units for the flows and mole fractions for the compositions. And if you don't do the conversion of these mass fractions to mole fractions, just leave that area blank right now. We'll talk about that in a moment. But please pause the presentation and draw and label the process flow diagram to the extent that you can. Well, I sure hope that you paused and tried to do this. So here's what I believe you should have drawn. So we have a reactor here. We have a feed to the reactor and a product. We're told that the flow rate of this product is 350 moles per minute. That product sent to a separator where we condense the methanol out to produce the stream that you see here. The vapor that's left is recycled and mixed with the fresh feed to the fresh feed, that's the overall feed to the process to produce the reactor feed. So let's go around and see what we know about each of these streams. So for the fresh feed, we know it's just a mixture of CO and hydrogen. So there's no methanol. Now these X's here are meant to represent mole fractions, not mass fractions. So there's no methanol, so if we use X1 to represent the composition of CO, then the composition of hydrogen is just 1 minus X1. After mixing with this recycle stream, we produce a stream with unknown flow, N2, and the composition of CO is unknown, we'll represent by the variable X2. The composition of hydrogen is unknown, represent that by X3. And we know that the sum of these have to add up to 1, so the composition of methanol is just 1 minus the other 2. The stream that comes out, we're told that it has a flow rate of 350, but we're not given these explicitly. We're not given the mole fractions of the 3 components, we're given the mass fractions. We're going to do that conversion on the next slide. So I'm just going to leave these blank for now. Put a little question mark there. From the separator, we know that this stream here is pure methanol. There's no CO, there's no hydrogen, and the mole fraction of methanol is 1, but we don't know its flow. The recycle stream, we're told, has 0.4% methanol on a molar basis, so the mole fraction is 0.004, but we don't know the flow rate, nor do we know the composition of CO, nor the composition of hydrogen. The composition of hydrogen we can calculate by taking 1 minus the composition of CO and minus the composition of methanol to get 0.996 minus X4. Now let's tidy up this problem a little bit and calculate what these mole fractions are from the mass fractions. We're going to have to go back to an earlier lecture in order to remember how to do that, but I'll remind you on the next slide. So how do we convert mass fractions to mole fractions? This slide was taken from a previous lecture. It's exactly the same. The way we do this is we assume we have a basis of 100 grams of the mixture. Then we list the components in that mixture and their mass fractions. The values you see here for carbon monoxide, hydrogen, and methanol are exactly what we're given in the problem statement, and they all sum up to 1. What we'll do is that if we have 100 grams of the mixture, we'll calculate the grams of each of these by taking 100 times the mass fraction. So for instance, the mass of CO and 100 grams of the mixture is 100 times 0.64, which is 64. The rest are computed the same way. The sum, of course, has to be 100, because we assumed we had 100 grams to begin with of the mixture. Next in this column, we identify and list the molecular weight for each of the species. For CO, the molecular weight is 28. For hydrogen, it's 2. For methanol, it's 32. From the molecular weight and the definition of molecular weight, we can calculate the number of moles of each of these species by taking the mass in this 100 grams of mixture, which we calculated in this column here, and dividing by the molecular weight. So for instance, for CO, we have 64 grams in the mixture. We divide that by the molecular weight 28 to find that there are 2.286 moles in that 100 grams of the mixture. Likewise, for hydrogen, 10.6 grams of hydrogen divided by 2 yields 5.3 moles of hydrogen. And for methanol, 25.4 grams of methanol divided by its molecular weight gives 0.794 moles. So the total number of moles of that 100 grams of the mixture, the total number of moles in that mixture is 8.379 by summing these up. The mole fraction is just given by taking the moles of each. So for instance, for CO, 2.286 divided by 8.379, which yields 0.273. We do the same thing for hydrogen and methanol. Take the moles, for instance, 5.3 for hydrogen divided by 8.379 to get the mole fraction. And do the same thing for methanol. Get the values you see here. A real easy way to check our work is just to sum these up. They should add up to 1. And fortunately, they do. Now we're going to transfer this mole fraction information to the process flow diagram. So you look at the process flow diagram, we filled in the mole fractions here on the process flow diagram. 0.273 is the mole fraction of CO, hydrogen's 0.639, and methanol is 0.095. Now what I'd like for you to do is to pause the presentation and perform a degree of freedom analysis for these 4 control volumes here that we have for this process. When we don't have a purge, we only have 4 control volumes. We don't have that split point. That was the 5th one. So for the overall control volume, I want you to do a degree of freedom analysis, assuming we'll do mass balances using atomic balances. For the mixing point, we're just going to do molecular species balances. We'll count the same way as we have in the past. For the reactor, we'll use atomic balances, and for the separator, we'll do molecular species balances. And to remind you that when we perform atomic balances, the degrees of freedom are calculated by taking the number of labeled unknowns and subtracting from it the number of independent atomic species, and then the number of independent inert species, and then any other equations that we might have. So now what I'd like for you to do is to take a moment and perform the degree of freedom analysis for each of these control volumes. Instead of showing the results for all of them, I'm just going to go through them one at a time. And we're going to start with the overall control volume, for which we're going to perform atomic balances because it has a reactor in it. So if we count the number of unknowns, we'll just go around the control volume and look at each of the streams that cross the boundary of that control volume and identify the unknowns in it. So let's start over here for the fresh feed. In this stream, there are two unknowns, N1 and X1. So N1 and X1 are added to our list over here. As we go around the control volume, the only other stream that crosses that control volume is the product here of our methanol. In this stream, we know it's pure methanol, but what we don't know its flow, N3. So we'll add N3 to our list of unknowns over here. Therefore, we have a total of 3 unknowns for this overall control volume. Let's count the number of atoms. We can do that by looking at the species that enter and leave. We find that each of these species enters and leaves the process. So the atoms that we have in here are carbon, oxygen, and hydrogen. So there's 3 of them. We might initially assume that all 3 are independent. So let's do that. Let's just assume they're all 3 independent. So we'll put 3 here. We'll put a minus sign in there. There's no inerts in the inlet or outlets to this control volume, so we'll go minus 0. We sum these all up. 3 minus 3 is equal to 0. Looks like we can solve it. Turns out we can't. The reason we can't is that carbon and oxygen appear in a 1-to-1 ratio in the reactant CO. They appear in a 1-to-1 ratio in the product methanol. Because of that, not all of the equations are independent. Let's actually verify that, and I'll show you what we really mean by that. To do that, let's do a carbon balance. We agreed that we're going to be doing atomic balances for the overall control volume as well as the reactor control volume. So we're going to count the number of atoms of carbon that enter and set it equal to the number that exit. There's only one stream that enters, that's the stream over here, and there's only one species in the stream that contains carbon in it, and that's the CO. So if we know the number of moles of carbon monoxide that enter, that's what this NC1 is going to represent here, and multiply by that by 1, that's the number of moles of carbon that enter. We're going to set that equal to the number of moles of carbon that exits. So if we look over here, there's methanol exits here. The flow rate of that methanol in the stream we're going to write as NM3, and for each molecule of methanol we have 1 carbon, so we'll put a 1 in front of it. So our carbon balance is a statement that NC1 equals NM3. Now let's look at the oxygen balance. The oxygen flow rate that comes in over here is going to be the flow rate of carbon monoxide. That's the only species that has oxygen in it. It's going to be a flow rate of carbon monoxide times 1, since there's 1 atom of oxygen per molecule of carbon monoxide. What comes out in the product here, the only thing that comes out is methanol. So we'll write down the number of moles of methanol that comes out, NM3, and there's 1 atom of oxygen per molecule of methanol, so we'll put a 1 here. Now look at these 2 equations that we have written for carbon and for oxygen. They're exactly the same. We can't use these 2 equations to solve for one of the unknowns. It's impossible to do that because they are exactly the same. The fact that oxygen and carbon are identical means that we can't use this overall control volume to solve for any of the unknowns. We're stuck. We're going to have to look at the other control volumes to see if we can start someplace else. For completeness, the atomic balance for hydrogen is shown here. Hydrogen enters only with the hydrogen in the inlet stream, so if the flow rate of the hydrogen molecule is NH1, multiply by 2 atoms of hydrogen per molecule of hydrogen, get the flow rate of hydrogen coming in. Hydrogen exits in the methanol. The way we calculate the flow rate of hydrogen out is taking the flow rate of methanol times 4 atoms of hydrogen per molecule of methanol. And so this equality here says that the amount of hydrogen that comes in is equal to the amount of hydrogen that comes out. So now let's look at one of the other control volumes. We'll just progress our way through until hopefully we find one for which we can solve the mass balance equations and obtain some of the unknowns. Next thing, let's look at the recycle point. The recycle point shown here, there's a control volume drawn around it. To do a degree of freedom analysis for the recycle point, we count the number of unknowns and compare it to the number of species. This is what we originally learned to do in the absence of chemical reactions. So if you go around the streams that enter and leave this control volume and count the number of unknowns, you find there's 7. I'm not going to go through that. I believe you can do that on your own. If we could look at the number of species that are present, we have CO and hydrogen coming in here. We have methanol coming in the stream, the recycle stream. So there's 3 species that come in and all 3 exit, so there's a total of 3. If we take the 7 unknowns and subtract the 3 species equations we can write, we find that there are 4 degrees of freedom in the absence of any other specifications, so we can't solve the mass balances for this control volume. We're going to have to keep on going and looking at the other control volumes to see if we can find one for which we can solve the balances. Next, let's look at the reactor. For the reactor, we're going to do atomic balances. In order to perform a degree of freedom analysis, we're going to count the unknowns for the streams that enter and leave, count the number of independent atoms, and then the number of inerts, and sum them all up. So let's do that. If we look at the stream that enters, I'm not going to go through all this with you, but you see there's 3 unknowns associated with that stream. For the stream that exits, there are none. So we have a total of 3 unknowns. We have 3 atoms if we just count them. So we might attempt to put a -3 here. And since there's no inerts, when we sum these all up, we find the sum is 0. But we have exactly the same problem we had with the overall control volume. The carbon and oxygen balances are identical. So we cannot solve for any of the unknowns with this control volume. If you remember, the reason that they're the same is that the ratio of carbon to oxygen is the same in the reactant CO as it is in the product methanol. And these do not appear in any other reactant or product. It's unfortunate, but that's the case with this particular problem. Finally, we're really hopeful now is that we'll be able to solve the balances for the separator here. We're going to be performing molecular balances. In order to see if we can do that, we'll count the number of unknowns. If we look at the streams that enter and exit, we find that there are 3. And we're also going to count the number of species. We have carbon monoxide, hydrogen, and methanol, and the 3 that are there. So if we take the 3 unknowns and subtract the 3 independent species, we find the sum is 0. And it appears the problem is solvable, and in this case, it is. We will be able to solve for the unknowns. We'll be able to solve for the flow rate of the methanol coming out, N3, for the flow rate of the recycle stream, N4, and the fraction of that stream, which is CO, X4. So what I would do is recommend that you pause right now and write down this molecular species balances for carbon monoxide, for hydrogen, and for methanol for the separator control volume that you see here. Well, I hope you did, because here's the results. What we're going to be doing is saying that N is equal to out. There's no reactions, and it's at steady state. So let's look at we have actually 4 choices for the balances we can write. We can write an overall, a carbon monoxide, a hydrogen, and a methanol. So let's look at all 4 of these and see if we can solve any one of them for one of the unknowns. So overall, we'll say is what comes in is the 350 from the reactor. That's equal to N3 plus N4, the total amount that comes out. If we look at CO, CO enters in the reactor effluent. The amount of CO is the fraction of that stream, which is CO, 0.273, times the flow rate of that stream, 350. Just to remind you, to calculate the flow of a species, we're going to take the fraction from below the arrow and multiply by the amount above. We'll set that equal to the amount of CO that exits in these 2 streams. There's none in this stream, which is pure methanol. The amount of CO in this recycle stream is going to be X4 times N4. Well, so far, we haven't really found one equation we can solve for one of the unknowns. This first equation has 2 unknowns in it. The second one has 2 unknowns. If we look at hydrogen, we do a balance for hydrogen. I'm not going to go through that with you. I believe you should be able to do that. We find that this 2 has 2 unknowns, X4 and N4. And if we look at the methanol, we find this last equation, this last balance also has 2 unknowns, N3 and N4. However, if we look at these, we could potentially solve the methanol balance with the overall balance for N3 and N4 simultaneously. Or we can do is combine the CO balance and the hydrogen balance in order to solve for N4. You might not see that right away, but this N4 gets multiplied through the parentheses, so we have a minus X4 N4 here, and then a 0.996 times N4. This X4 N4, when added with this one, will cancel. Let's see what we do on the next slide. This next slide shows those 4 equations reproduced here. What we're going to do is we're going to add the CO and the hydrogen balance. So if we do that, we add the terms on the left-hand side. We have 0.273 times 350 plus 0.632 times 350. So if we add these 2 fractions together, we get 0.905 times 350. That's going to be equal to the sum of what's on the right-hand side. We have 0.996 times N4. Then we have a minus X4 N4 when we distribute the N4 across the parentheses. When added to the CO balance, this X4 N4 cancels that X4, N4. So all we're left with is 0.996 N4. This equation we can solve easily for N4. It's 318. And that's shown here on the diagram. If we use the overall balance, we can solve for N3. It's just 350 minus N4. That's 32, which is shown here. And finally, we can calculate X4 from the CO balance. It's 0.273 times 350 divided by N4, which is 318. That gives us 0.3. So all that information is in red here, been added to our process flow diagram. Now let's go back and examine the other control volumes and see if there's one that we might be able to solve the mass balances for. Which one do you think it is? Well, let's look at the overall control volume. And for this overall control volume, we're going to use atomic balances. And we're going to write those in terms of flows instead of compositions because the problem's easier to solve that way. We can do it either way, it's just that it's easier to actually solve the equations for the unknowns when it's written in terms of the flows. So we're going to let the flow rate of N sub CO represent the flow rate of carbon monoxide. That's going to be equal to X1 times N1. And we'll let the flow rate of hydrogen be represented by the variable N sub H, which is 1 minus X1 times N1. So if we look at our control volume here, we're going to say all the carbon, the moles of carbon atoms that enter is going to be equal to moles of carbon that exit. So we have CO that enters, so the moles of NCO, the molecule enter, we multiply by 1 carbon per molecule to get the moles of carbon that enter. That's going to be equal to moles of carbon that exit. We know that there's 32 moles that exit of the stream in total. The flow rate of methanol is 1 times 32, so that's 32 is the flow rate of methanol, and there's 1 carbon per molecule of methanol. So that's carbon in equals carbon out. NCO is just 32, shown here. If you look at the hydrogen, there's 2 atoms of hydrogen per molecule of hydrogen, so we'll take 2 times the flow rate of hydrogen coming in. That's going to be equal to hydrogen coming out, which is the flow rate of methanol, 32, and there's 4 hydrogen per molecule of methanol. Equating these two together, we're able to solve for the flow rate of hydrogen coming in at just 64. We do the same thing for oxygen. Oxygen comes in the CO. We have to take the flow rate of CO coming in, multiply by 1 atom of oxygen per molecule of CO. Set that equal to oxygen flowing out in the methanol. There's 1 atom of oxygen per molecule of methanol. We'll multiply then that 1 by the 32, the flow rate of the methanol coming out, which leads us to see that the flow rate of which is exactly the same equation as the equation for the carbon balance. So we just confirmed that the flow rate of CO is 32. Now to calculate X1, we just take the flow rate of CO divided by the sum of the 2 flows here, which is the flow rate then of the fresh feed to the reactor. So 32 divided by 32 plus 64 is a third. And as we just noted, the carbon and oxygen balances are identical, and they both tell us that the flow rate of CO is 32. Now, let's move on to the mixing point. And if we look at the mixing point here, we should be able to solve for the flow rate of that leaves the mixing point N2 by doing an overall mass balance. And we'll be able to calculate X2 and X3 by doing balances on the 3 species. 2 of those balances on the 3 species will allow us to solve for X2 and X3. And then finally from that, we're going to be able to calculate single pass conversion and overall conversion from the definitions of these 2. Let's go back and review this. A single pass conversion is equal to, and we're going to calculate this in terms of the single pass conversion of CO. It's going to be equal to the amount of CO that enters the reactor. The amount of CO that enters is X2 times N2. And we're going to subtract from it the amount that exits, which is 0.273 times 350. That's the amount that reacts. We're going to divide that by the amount that enters. So single pass conversion is N minus out divided by what goes in to the reactor. The overall conversion is written in terms of the process, so for the overall control volume. The amount of CO that enters, the overall control volume, is in the fresh feed. The amount is 0.333 times 96, that's N. What comes out in this product stream is nothing, 0. So we have N minus out for the overall control volume, and we're going to divide that by the amount that comes in. We already know enough here to calculate the overall conversion. It's 1. all of the CO that enters eventually reacts because we don't pull any CO out. The product stream contains only methanol. However, when you do the calculations for the reactor, the single pass conversion calculations here, what you're going to find is that single pass conversion is less. Why don't you take a moment and do that? Solve the mass balances for around the mixing point there for X2, X3, and N2, and then calculate the single pass conversion. If you do solve those mass balances, I'm not going to reproduce them here, what you find is that the sum of these two flow rates gives a flow rate going into the reactor is 414. You can calculate the composition of CO going in as 0.308. So if we take and substitute those numbers in here into our single pass conversion calculation, we find the single pass conversion is 0.25. So about 25% of the CO that enters into the reactor is converted. What does not react gets removed in the separator and gets recycled back. If you have questions about this, please ask in class. Next time, we're going to be working reactor recycle problems in which we have to have a purge stream to remove an inert. Bye for now.